language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass of NN module. And then I'm calling it and I'm passing in the inputs and the targets. And I'm just printing. Now, when the inputs and targets come here, you see that I'm just taking the index, the inputs x here, which I renamed to idx, and I'm just passing them into this token embedding table. So what's going on here is that here in the constructor, we are creating a token embedding table, and it is of size vocab size by vocab size.
Okay.
And we're using NN.embedding, which is a very thin wrapper around basically a tensor of shape vocab size by vocab size. And what's happening here is that when we pass IDX here, every single integer in our input is going to refer to this embedding table and is going to pluck out a row of that embedding table corresponding to its index. So 24 here will go to the embedding table and will pluck out the 24th row. And then for 43 will go here and pluck out the 43rd row, etc.
Okay. So that is the context vector that we talk about, right? We initialize it. What we did, video one, we did something of that sort, I believe. No, I think it was all around back propagation. So intention is to reach somewhat here. I don't see this, that. But initially the intention is that we haven't seen, we just randomly initialize that vocab by vocab size vector, and we then go around training it. Anyway, let's go ahead and do that. So
And then PyTorch is going to arrange all of this into a batch by time by channel tensor. In this case, batch is 4, time is 8, and C, which is the channels, is vocab size, or 65. And so we're just going to pluck out all those rows, arrange them in a B by T by C, and now we're going to interpret this as the logits, which are basically the scores for the next character in a sequence. And so what's happening here is we are predicting what comes next based on just the individual identity of a single token. And you can do that because, currently the tokens are not talking to each other and they're not seeing any context except for they're just seeing themselves. So I'm a token number 5, and then I can actually make pretty decent predictions about what comes next just by knowing that I'm token 5, because some characters follow other characters in typical scenarios. So we saw a lot of this in a lot more depth in the makemore series. And here, if I just run this, then we currently get the predictions, the scores, the logits for every one of the 4x8 positions. Now that we've made predictions about what comes next, we'd like
for shift 65.
to evaluate the loss function. And so in makemore series, we saw that a good way to measure a loss or like a quality of the predictions is to use the negative log likelihood loss, which is also implemented in PyTorch under the name cross entropy. So what we'd like to do here is loss is the cross entropy on the predictions and the targets. And so this measures the quality of the logits with respect to the targets. In other words, we have the identity of the next character, so how well are we predicting the next character based on the logits? And intuitively, the correct dimension of logits, depending on whatever the target is, should have a very high number, and all the other dimensions should be very low number, right? Now, the issue is that this won't actually, this is what we want. We want to basically output the logits and the loss. This is what we want, but unfortunately, this won't actually run. We get an error message. But intuitively, we want to measure this. Now, when we go to the PyTorch cross-entropy documentation here, we're trying to call
XP and YB are stacks of numbers. Okay. We're passing on okay. What's happening there?
the cross-entropy in its functional form. So that means we don't have to create like a module for it. But here when we go to the documentation, you have to look into the details of how PyTorch expects these inputs. And basically the issue here is PyTorch expects, if you have multi-dimensional input, which we do because we have a b by t by c tensor, then it actually really wants the channels to be the second dimension here. So if you, so basically it wants a b by c by t instead of a b by t by c. And so it's just the details of how PyTorch treats these kinds of inputs. And so we don't actually want to deal with that. So what we're going to do instead is we need to basically reshape our logits. So here's what I like to do. I like to basically give names to the dimensions. So logits.shape is b by t by c and unpack those numbers. And then let's say that logits equals logits.view, and we want it to be a b times t by c. So just a two-dimensional array, right? So we're going to take all of these positions here, and we're going to stretch them out in a one-dimensional sequence.
Which height? 65. Got it.
And preserve the channel dimension as the second dimension. So we're just kind of like stretching out the array so it's two-dimensional, and in that case it's going to better conform to what PyTorch sort of expects in its dimensions. Now we have to do the same to targets, because currently targets
Okay, target.
are of shape b by t, and we want it to be just b times t. So one-dimensional. Now, alternatively, you could always still just do -1, because PyTorch will guess what this should be if you want to lay it out. But let me just be explicit and say view times t. Once we've reshaped this, it will match the cross entropy case, and then we should be able to evaluate our loss. Okay, so that right now, and we can do loss.
Okay, let's go through it. What is happening? The time being we want XP and YB. So I will just pluck out the imports that he has done. So these are the imports initially. Plus icon language model, and then we'll just explain what's happening in the internally. Okay, super dot underscore init underscore c. uh in the initial first class, if you remember, right, it was here, I believe. Okay, so these were the characters that we are getting, and bigram was representing the whole of this probability. Okay, but if you remember, we always used to create that bigram yeah, something like this. Okay, this what you see here, right? Initially the initialization was, oh, not this one, sorry. This is not the correct. Let me explain it here itself. So 65. Oh, let's start with small. 6 cross 6. I think it was. Okay, so let's say we have 6 words in the vocabulary. Okay, vocabulary size is a 6. We have 6 words. Each of the row that you see, right, represents each word. Okay, each of the row represents each word, and let's take okay, and say A has been given an index of 1, B has been given an index of 2, C has been given an index of 3, D has been given an index of 4, E has been given an index of 5, F has been given an index of 6. Okay, now um, for each of these index, whatever we receive, right here it is, say we are getting it as 24. Um, whatever number we receive, right, we make that as a 1 here. So first one, right, let's say the first row, if it has to represent 0, right, it should have started with okay, let's just add one more example, because usually indexing starts with 0, right, and let's make it 7 cross 7. Okay, that is what is token embedding table. Okay, I will just put this thing here so that we don't. So this is the 7 cross 7. Let's take the first one. Okay, first one is one of the examples. So first one is 0 comma 0 comma 0 comma 0 comma 0 5 6 7. So if it has to represent a, right, this is what we'll make it as 1. Okay, means we are doing a one hot encoding. That's what it is. Next is if we want to represent, say, E is the character that is coming. E is the character that is coming. All zeros. What will be fifth? 0, 1, 2, 3, 4, 5. Fifth is 1. So like this, right? Uh, we will, so here it will be 1. Here it will be 1 for E. In that way, we'll go on representing one hot encoding of each of the characters that are coming in with us. Okay, so that's what he's doing here. So we are passing it xb. Okay, what does xb represent? If you just see, so xb represent each of these characters, means it is 4 cross 8. Now what you're doing, this 24 that you are seeing here, right, it will be represented like this with 65 length array, because we have vocabulary size is 65 here. That's what we got, right? So this was the length, was vocab size is 65 here. So what will happen, each of these numbers, right, so what's happening here is, so you can think of the 0 1 2 3. So we have 4 is the batch size. Okay. In each batch, how many examples we have? We have block size number of examples. That's it, right? We have block size. So it is 8, 3, 6, 8. So this is 0, 1, 2, 3, 4, 5, 6, 7. Those are 8. Okay. And for each of those examples, say what you see here as 10, right? This is 24. Okay. Now to represent this 24, right, what we are doing is we are taking, this is 65 length. Okay. So here if you see, right, 0, 1, 2, 3. So this is 0, 1, 2, 3 to 65. This axis. Okay. And we have assigned 24th. So here there will be somewhere around 24th index and we are making it as 1 and all other zeros. So it's a way to represent that is the 24th element. In the same way, if we have to talk about 43, right? So this means in place of this 22 that you see here, right? 22, we have 43. 43 is there, and again it has 65. This has 65 these one after the other, and 43rd of that, right, will mark as one. So like that, it will be 4, 8, 65. That's what this embedding will do. We can check that as well. So self dot token underscore embedding underscore table equal to nn dot embedding, sorry, vocab size, vocab underscore size. Okay, and oh sorry, this is definite. I forgot. Def init um, targets logits equal to self dot um, token underscore. So one hot embedding is what we are doing. Indexing table. Let's see what we get. Sorry. Return logits. Okay, so we will do m is equal to m is equal to bigram language model. We are passing it the vocab size. Let's do, sorry, let's do one thing. Yeah, okay. M we will pass xp comma yb. As of now we are not using. Okay, we got it. Now let's do chats. So as I told, 4 block sizes, 8 here, 65 here. Okay, now let's see. XP we printed, right? So first was 24. Okay, so if I need to see what how this 24 is represented here, right? Logits If you do a 0, it takes this red one, this 8 cross 65, it will come. We can print that as well. So this is 8 cross 65. Okay. In that, no, this is not one hot embedding for sure. Okay, we are not representing in this way. Yeah, we are doing it. Oh, represent. Okay, so we have taken the representation based on the numbers. Each, this is 3 is the size. Oh, we are not doing, we are doing embedding. Okay, sorry for that. So each character, context, length, there it is 8, here it is 3, and each of them we are representing using 4 embedding size. Oh, okay. So this is randomly generated, okay. So what is happening is, so these are random numbers that are coming here. Let me check what is an embedding. So this is the sparse matrix, okay. Um, And embedding layer is just a linear, so okay. Got it. How to explain this thing? This is what is happening there, okay? Um, okay. So the thing that's here is we have this array, okay? XB, okay? This array XB here, I will just write it out. XB, okay? And now we have something known as this table. So it can be where it went, m dot m. Okay, it's an embedding table. Um, I don't know. So this is 65 cross 65. Okay. Now we are doing something like for each of the row, sorry, for each of the row, for each of the element, say 24th, we are plucking out 24th row from here. So if I give you 24, right? So we get this value. Okay, right? And if you go here, you see the same value coming here. Okay, 176, 176,247. So what's happening is, this is like a lookup table, you can see. Okay, and this is generated randomly, and this is what something we are going to train. Okay, so what's happening here is we have created a 65 cross 65 vector. The intention again is we want to represent each of this word in this bigger size of an array. Okay, now this xb, it says first element is 24th. How we are going to represent that element? We will pluck out the 24th row from here. That's what I did, and you get this. Okay, so that's what you see here. So 24 is represented using this. Next xb we had was 43. So what is happening? 4, that is 4 cross 8. Okay, and this is 65 it will become. So first, in place of 10 we had 24. That 24 is getting represented, sorry, 24 is getting represented using this 65 size array. And this is random. Okay, initially it's random. This is something that we will train as we go ahead. So this is one. What was the next thing? Yeah, so I was saying that is 24. Next is 43rd. 43rd by, I mean 20, 22 that you see, right? That is like um 43 is written there. Okay, and for that the embedding will be 43. So this is 33239594. So 33239594. So like that, we are creating 4 cross 8 cross 65 for each of the element that are coming here. And that's what we are doing here as well. So for each of these many rows, we had 3 numbers. So this is 2,28,146. So 2,28,146. They are, just to be much more efficient and everything, we are doing it in batches. So 2,24,186. This is 3. This is 3. And this is the lookup table. So for each of those elements that are coming here, we are plucking out 20, sorry, 4 rows from there. So this will be equal to 2 like 3 and 4. Okay. So that's why when we do it right, we see batch size, number of block size, and each block represented using 65 cross representation. Okay, so that's what embedding vector is doing. So that was one thing. So that's what we got. Now the problem that we were facing is we have targets. Okay. Okay, so we have targets as well. Sorry, it's not target, it is IB. which looks something like this. And okay, so 43. So it means if we and the input that will go hmm, okay, so this is how we are going as an input. Okay, each of those 8 that you see right in a particular batch, for each of those 8 we will get a probability distribution, and we need to calculate the loss if we are getting 43. So it means if I am giving in 24, okay, am I getting 43? If no, train it. Okay, calculate the loss of what we are getting, because this is a bigram model. Okay, so and then there is an issue with the shape here. So we are doing B cross T. That means rather than being 4 cross 8, right, it will become 4 into 8, 32 will become, and all 65 will come here. So um, this row of 10 7 4 1, the next will be say 22 19 16 13, the next will be 11 8 5 2, next will be 23 20 17 14. So like all of these what you see right chunk will start sitting next to each other. Okay, again the intention is that for each of these we'll try to make a prediction and calculate the loss and everything and go ahead with that. So B T C will get all the logits dot shape, and then logits dot view B cross T cross C. Okay, so how it is looking is logits is like this. Okay, let's not take that. So logits 0. So these were the 8 examples. Sorry, 8 examples across. So 0. I am taking this 8 such pillars for 0th this thing, a red 0 that you see here. Okay. Now when I do logits dot view, um, wait, how this sit next to each other is something I will see. So logits dot view. So B cross T cross say temp underscore logits. Okay. You are getting the first element as I told. So this is where it is. This element that you see should be placed next to it, or it can be other way around. Let's see how it is placing it. So you are getting this element. So rather than these getting stacked across that blue line, all are getting stacked across the red line itself. Okay. So that's what view does to it. Sorry. So that is happening. Now targets also, what I am doing is, it's a B cross T. It's a 2D array. Okay, it's YB. Okay. Um okay, we don't need to embed YB. Yeah, okay. So for each of these lines, now we are just getting across red line. Is there a way to check it? Mm. So rather than this, right, it has become like this. So one dimension it has gone for DOS. So this is what has happened. Uh, so all are sitting one after the other. Okay. 1, 2, 3, 4, 5, 6. Oh, it has become like this. So you can. Okay, for the time being, so you can think of it as the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this, one after the other it has planed. And for each of them, right, we have a target, 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 target. So YB was also like this. So we are putting one after all of this in one shot. So what will happen? Targets dot view B cross T. So YB dot view B cross T. See, 43, 58, 39 till 39, then 53 gets added here. So all in one line. So this line will sit next to this. So this is uh, uh, 43 one pillar, 55 50, so 43 43 58. Oh no, sorry, this is YB. Means this thing what we were getting here, right? Logits. So what is happening? So 32 cross 65 we have, and it is 30. So each 32, sorry, each of these 32 we have, and each is 65 in length. So 1, 2, 3, 4, 5, something like 65 columns are there. For each of those columns, we have 32 targets to it. 32 targets that are sitting next to it. Targets we got, and then loss equal to f dot cross entropy. That's loss. Loss.
And so currently we see that the loss is 4.87. Now, because we have 65 possible vocabulary, the loss should be. And in particular, we covered negative log likelihood in a lot of detail. We are expecting log or ln of 1 over 65 and negative of that. So we're expecting the loss to be about 4.17.
It's like we make. Yeah, I would understand what you're saying, right? So if this, rather than doing this embedding and all random, right? If it played all of them as one, okay, and compare it with the target. The worst case will be 1 of 65. At least that I mean, if we're able to do better than that, that's when it is good. Okay, right?
But we're getting 4.87. And so that's telling us that the initial predictions are not super diffuse. They've got a little bit of entropy. And so we're guessing wrong. Yes. But actually, we are able to evaluate the loss. Okay, so now that we can evaluate the quality of the model on some data, we'd like to also be able to generate from the model. So let's do the generation. Now I'm going to go again a little bit faster here because I covered all of this already in the previous videos. So here's a generate function for the model. So we take the same kind of input, IDX here. And basically, this is the current context of some characters in some batch. So it's also B by T, and the job of generate is to basically take this B by T and extend it to be B by T plus 1, plus 2, plus 3, and so it's just basically, it continues the generation in all the batch dimensions in the time dimension. So that's its job, and it will do that for max new tokens. So you can see here on the bottom, there's going to be some stuff here, but on the bottom, whatever is predicted is concatenated on top of the previous IDX along the first dimension, which is the time dimension, to create a B by T plus 1. So that becomes the new IDX.
B cross C. Okay. Hmm. Okay.
So the job of generate is to take a b by t and make it a b by t plus 1, plus 2, plus 3, as many as we want, max many tokens. So this is the generation from the model. Now, inside the generation, what are we doing? We're taking the current indices, we're getting the predictions. So we get, those are in the logits.
So logits is 32 cross 65. Okay. So that means this 32 cross 65 will get like that, and we are calculating the loss as well. Now focus only on the last time stamp. Become B, comma C. Okay, let me logits. We get 32 cross 65 colon. It means all the rows minus 1. This it took. Why we need again a comma? That's what, right? Yeah, you don't need that. So it will return the last index.
And then the loss here is going to be ignored because we're not using that, and we have no targets that are sort of ground truth targets that we're going to be comparing with. Then once we get the logits, we are only focusing on the last step. So instead of a b by t by c, we're going to pluck out the -1, the last element in the time dimension, because those are the predictions for what comes next. So that gives us the logits, which we then convert to probabilities via softmax. And then we use torch multinomial to sample from those probabilities. And we ask PyTorch to give us one sample. And so IDX next will become a b by 1. Because
Oh, okay. And function that's doing that later.
in each one of the batch.
So what's happening is def generate. So idea new underscore tokens for underscore and range budgets comma loss self IDX. Sorry. Okay, this calls, this is it.
Dimension.
So here that is what is happening. It shows this.
We're going to have a single prediction for what comes next. So this num samples equals 1 will make a sampling process according to the probability distribution given here. And those integers just get concatenated on top, calling self of IDX, which will end up going to the forward function. I'm not providing any targets. So currently this would give an error because targets is sort of like not given. So targets has to be optional. So targets is none by default. And then if targets is none, then there's no loss to create. So it's just loss is none. But else, all of this happens and we can create a loss. So this will make it so if we have the targets, we provide them and get a loss. If we have no targets, we'll just get the logits. So this here will generate from the model. And let's take that for a ride now.
It just tokenizes it and we are getting it here. is printing. Okay, logits is getting printed. Um, Three-dimensional. No, it's not. Oh, cross 8 cross 65. How come it's happening? Oh, we do this. Because here it should have.
Oops. So I have another code chunk here, which will generate for the model, from the model. And okay, this is kind of crazy. So maybe let me let me break this down. So these are the IDX, right? I'm creating a batch will be just one, time will be just one. So I'm creating a little 1 by 1 tensor, and it's holding a 0. And the D type, the data type, is integer. So 0 is going to be how we kick off the generation. And remember that 0 is the element standing for a new line character. So it's kind of like a reasonable thing to feed in as the very first character in a sequence to be the new line. So it's going to be IDX, which we're going to feed in here. Then we're going to ask for 100 tokens. And then n.generate will continue that. Now, because generate works on the level of batches, we then have to index into the 0th row to basically unblock the single batch dimension that exists. And then that gives us a time steps, just a one-dimensional array of all the indices, which we will convert to simple Python list from PyTorch tensor, so that that can feed into our decode function and convert those integers into text. So let me bring this back, and we're generating 100 tokens. Let's run. And here's the generation that we achieved.
The only thing for me is the shape, right? gives me the token. Here I'm not positive, so it's none, loss is none. Okay. So we will pass it, and so if I give it as a generate as a 0, okay, it will how we were doing here, right? It was taking each of the element from here and plucking out that particular row from here. That was the intention, right? The same thing from this table, right? We're trying to pluck out that particular row, the index from there. So I think it should be zeros, but anyway. So 1 cross 2 also if I do right, see. Mm. That's what it was as well, right? Okay. D type equal to int. Not sure if it works or not. Ah, it worked. It can't take a float, right? Because it has to pluck out this row. So 0.0 is, it can't be a row. 0 will be a row. It will be same because both are 0, 0. So what's happening? This line is first giving me the embedding. So here, because we don't need to calculate loss and all of those things, right? I'm printing and the logis dot shape is 1. So each of these are getting represented as 65 element arrays. Okay, now that is 65. Got that. Now if you want to generate, we'll pass on just one element, and it will give us the space and everything for the 0th row. We have the logits here, and this will be 1 cross 1 cross 65. So 1 cross 1 cross 65, something like this itself. So this one building that will be standing. then he does something interesting. So it becomes a 1 cross 65 rather than having 1 cross 65. It is 1 cross 65. That's understood because that's the input vector that we will be taking. So this is the embedding. One cross 65 it happened. Then we did 65, then we calculated logits or the probabilities. No, we did a softmax across dimension 1. So that gave me a single element, right? Because, no, softmax, what was the formula? I think it gives me some. This is the probability that I got using the softmax. Then I did a multinomial based on the probability. I pluck out one sample that gave me 31st row of whichever was that 1 cross 1, and previously it was 0 that I started with, that is here. I have added 31 to it, and that has become a 1 cross 2. Okay, we don't need to break. Return IDX. So these are the arrays that come 0, 35. I mean, it's okay, because that does for the batches. O equal to like this. Then O is this. It's a 2D array. So if we do 0, this becomes a 1 array. Decode, we can put it in there. How come it is possible? 0, we have no slash n. Oh, okay. That doesn't understand tensor. Slash and DMCL. If I do a print, it will print the slash in the next line. I believe. Yes. This is what my model predicted.
So obviously it's garbage, and the reason it's garbage is because this is a totally random model. So next up, we're going to want to train this model. Now, one more thing I wanted to point out here is this function is written to be general, but it's kind of like ridiculous right now because we're feeding in all this, we're building out this context, and we're concatenating it all, and we're always feeding it all into the model. But that's kind of ridiculous because this is just a simple bigram model. So to make, for example, this prediction about k, we only needed this w. But actually what we fed into the model is we fed the entire sequence.
Yeah, that's that 4x8, right? 32 that we are doing. It's a bigram model, so just based on the last input that we are getting, right? We're making the prediction based on that. Generating an embedding for that, and is the prediction happening? My question was, where is this dot product happening? So when we do an inference, right? So loss is that where we are making the prediction is what I want to say. Only, but this is not the 10123. I think in the 4. Doing the training and everything is fine while doing an inference, right? All this is fine. Where is the inference part? Backprop Ninja. Oh, this is a different case altogether. So, wanna check during the inference, right? Oh, it gives us the logic itself is the expectation. Okay. When we pass on that model, right? It does all those dot multiplication and everything here. When we pass on to that, it does this multiplication, adds the bias, pulls that thing out for us. And this sequential is the one which does it one after the other. Sequentially are passing, but each. So it's like a linear layer itself that goes there, does the multiplication, and returns me the output. Okay. As of now, we are expecting that that itself is the table, but that will get changed. Yeah.
and then we only looked at the very last piece and predicted k. So the only reason I'm writing it in this way is because right now this is a bigram model, but I'd like to keep this function fixed, and I'd like it to work later when our characters actually basically look further in the history. And so right now the history is not used, so this looks silly, but eventually the history will be used. And so that's why we want to do it this way. So just a quick comment on that. So now we see that this is random. So let's train the model so it becomes a bit less random. Okay, let's now train the model. So first what I'm going to do is I'm going to create a PyTorch optimization object. So here we are using the optimizer Adam W. Now in the makemore series, we've only ever used stochastic gradient descent, the simplest possible optimizer, which you can get using the SGD instead. But I want to use Adam, which is a much more advanced and popular optimizer, and it works extremely well. For typical good setting for the learning rate is roughly 3e-4. But for very, very small networks, like is the case here, you can get away with much, much higher learning rates, 1e-3 or even higher probably. But let me create the optimizer object, which will basically take the gradients and update the parameters using the gradients. And then here, our batch size up above was only 4. So let me actually use something bigger, let's say 32. And then for some number of steps, we are sampling a new batch of data. We're evaluating the loss. We're zeroing out all the gradients from the previous step. Getting the gradients for all the parameters, and then using those gradients to update our parameters. So typical training loop, as we saw in the makemore series. So let me now run this for, say, 100 iterations, and let's see what kind of losses we're going to get. So we started around 4.7, and now we're getting down to like 4.6, 4.5, etc. So the optimization is
Because it is trying to make it work for not bigram but all different types of model, right? I think that's the reason why it looks this complicated. It would have been a bit easier, and that's what made me confused in terms of why bigram is going like that. So warning underscore size steps.
definitely happening, but let's sort of try to increase the number of iterations and only print at the end, because we probably want to train for longer. Okay, so we're down to 3.6 roughly. Roughly down to 3. This is the most janky optimization. Okay, it's working. Let's just do 10,000. And then from here, we want to copy this. And hopefully, we're going to get something reasonable. And of course, it's not going to be Shakespeare from a bigram model, but at least we see that the loss is improving. And hopefully, we're expecting something a bit more reasonable. Okay, so we're down at about 2.5-ish. Let's see what we get.
Need to pluck out next new token 100 words and tool is that we did here, and this needs to coincide decode.
Okay, well, dramatic improvement certainly on what we had here. So let me
1165. Apologies for that. Sorry for that. When we are trying to train the model, right, that is giving us the loss, and based on the loss we are trained back propagating. So this is taken care by the loss is getting calculated, and based on the optimizer we are changing the values of this embedding vector every time.